All right, thanks everyone, and thought I'd show you a few different things in the origami world, both on the science and math side, which is more my background, and on the sculpture side, which is something I've been pursuing a lot lately with my dad. And also, it's kind of fun to just show pretty pictures of sculpture and fashion and stuff. So we'll spend a bunch of time there. Um, as Eve mentioned, we wrote this book, Geometric Folding Algorithms. This is sort of I guess, started with my PhD thesis and became like this world of computer science and math meets origami. And if you're like me and you don't like reading books, you rather watch video lectures, I teach a class at MIT which has free videos online, and you can stream those and learn all about the stuff I'm about to mention. I started in this area in 1998, 1999. I don't know, those of you who were around then, there weren't smartphones, so there weren't very many cameras. This is one of the few pictures I could find of an early me folding some paper with Laura Kruskal, which if you know origami history, she did a lot to promote origami in the United States. She was daughter-in-law of Lillian Oppenheimer, who played an even bigger role in bringing origami to the West. And one of the first, I was a computational geometer looking for interesting problems to solve, and so one of the things I started to wonder about is what shapes can you fold? Can you fold any polygon from a square of paper? Or if I give you paper that's white on one side and black on the other, can I fold any two-color pattern? Or even more exciting, can I fold any 3D polyhedron? And we proved way back in 1999 that this is always possible. Origami is universal. From a large enough square of paper, you can fold any shape with any two-color pattern you want. But the algorithm we gave to do it was extremely impractical. You'd never want to fold something out of it. And it wasn't until about a decade later I met Tomohiro. He already told a version of this story, and we started working on proving that origamizers, both on the one hand a practical method you could use to actually fold things like this bunny, but we proved also it's universal and always works and seems to be quite efficient. We're always motivated by science fiction, so I watch a lot of movies and Transformers and Terminators. I want to make robots that can fold into anything. And one, on the other hand, Origamizer gives you a way to fold any one shape, but different shapes require different crease patterns. So we've also worked on how to make one crease pattern to rule them all, one crease pattern that can fold into any 3D shape. So here, for example, a n by n pattern can fold into about n different cubes. And so if you have any 3D shape made out of cubes, sort of like the 3D equivalent of pixelization, from a large enough sheet, you can fold many different shapes. This is actually not super efficient, but we have some more recent algorithms that more efficiently fold nice shapes like this car. Or if you start from a strip of material, then you can fold surfaces very efficiently. You just need a strip of material that's twice the surface area of what you're trying to fold. And then you can fold anything out of that one universal strip. Including, for fun, you can fold letters of the alphabet. So I have here, if I can find my other window, a little implementation of this where I can say fold EPFL, for example, from this long strip of material. Or if you wanted to do this in practice, you might take this square and cut along the black lines to make a strip. Anyway, once you have this idea, of course, you want to make robots that self-fold. So these are some examples of self-folding sheets where you apply some electrical current, different things heat up and cause folding, similar to some of the self-folding that Tomohiro showed, though these are some earlier versions, a little less advanced, but you get some pretty cool examples. Like the top right, we have a robot self-folding. Oops, sorry. And it will, after folding, for a few minutes, use the origami design to actually become a functional robot and start walking away. Obviously, we're still a long way from practical origami transformers and things like that, but it's a lot of fun to explore. One of the challenges with real life is that we have thickness in paper. One of the classic problems is how many times can you fold a piece of paper in half? until you can't anymore. And usually the answer is around 7 or 8. But if you start with a long enough piece of paper, like 3/4 of a mile, that's a little over a kilometer, then you can achieve the current world record, which is 12 times. This is after 11 folds here on the right. Probably will remain the world record until you can buy a piece of paper that's 2 miles long. And we have algorithms for taking most of the mathematical designs assume 0 thickness material, like this design here, and then by doubling the creases and offsetting them, we can extend that to work with thick material, which is one big thing that happens in the structural origami world when you actually want to implement these things. Here's a little example of that in real life. And now I want to transition to talking about sculpture, and the sculpture that my dad and I do is originally motivated by this mathematical problem of how pleats fold. And it's something we've been exploring over the last 27 years, I guess. And we kind of go back and forth between the math and the art side. And our starting point is actually from the Bauhaus in the late 1920s. There's this model in the top left that's now called the hyperbolic paraboloid in the origami world. It was pretty popular when I was just learning origami. And it's something we've folded thousands of, and it seems really cool. And we're trying to understand how exactly it works. Why does pleating along concentric squares, alternating mountain and valley, pop into this cool 3D saddle surface? And this is one of my first collaborations with Tomohiro. It turns out it doesn't even exist mathematically. It's impossible to fold a piece of paper with exactly this crease pattern. So that was kind of surprising and shocking. We can make something in reality that doesn't really exist in the pure sense. You have to stretch the paper. And so we kept exploring, what other kinds of pleat folding might make sense. And back to the Bauhaus, we don't know exactly who folded this. It's a student of Joseph Albers, again, late 1920s, concentric circles instead of squares. That seems cool. So we started folding these. You have to cut a little hole out from the center. It seems to fold much nicer, and conjecture this actually exists mathematically. We haven't been able to prove it, though we can with very high precision get very close to foldings. That's recent work with Klara Mondolova. But meanwhile, we explore what's possible sculpturally. So we'll take a bunch of these circular units and interweave them in fun ways. And there's kind of a back and forth with the material to see what we can assemble that with this kind of self-folding behavior of the material. And these are some larger examples, or this is my dad and I making a really big example just for a photo shoot, and then of course it all fell apart. But the idea is you can make pretty large structures by combining these sort of modular units. With curved creases, they're very strong, and can make really cool shapes. We also are glass blowers, so we make the same thing out of glass, or make glass containers to put our paper sculpture inside. My dad's background is actually as a glassblower. He was the first artistic glassblower in Canada. He's called the father of Canadian glass. And my wife, Marielle, is also a glassblower, and she makes more realistic forms. So these are some frogs we collaborated to make. And this is a giant glass brush, 5 feet long, call it 3 meters. 35 pounds. I'd like to say it's like 35 kilos, no, 20 kilos or so. And this is like a magical brush, we imagine, where you have the curved crease foldings inside the brush. And the bristles here are also made out of paper. And out of the bristles, you can see the strip folding font. So it's folding brush with words out of that. It's the first time we actually folded the strip folding font in reality. It took a very long time, days, I believe. A lot of our sculpture, we print some secondary message onto the paper before folding to give it a little more interesting message. This is, for example, the complete works of Shakespeare restricted to just the red words, words containing red in them, like feathered or dishonored. A lot of past tense. Here is from a recent TV show, Craft in America, where you can see some of this stuff in action. of making a new one of these pieces, embedding the paper into glass and also blowing the glass. Here is an imagined collaboration with Joseph Albers, who did the original, or one of his students did one of the original curved foldings. He also designed this print, which is like a abstraction of Manhattan skyline. We converted it into a circular design and then folded that into the circular creases. Here is something we did for 250th anniversary of Beethoven, using some of his hand-drawn scores. This is a more recent piece about freedom, something we need a lot of these days and don't have enough of. And I just wanted to illustrate, in making a piece like this, we use a lot of software tools to design the structure before folding. Here I wrote software just to lay things out in a circle, because most text programs are not designed for drawing in a circle until we got what we want. Or here's a more advanced version where we wanted to do something for vision impaired people, so they could have Braille text on the folded sculpture. This is with Alfonso Pararubio, who's in the audience there. And so in this case, we made you can see down in the bottom right here, designed Braille in a spiral. So you could read the text by moving your finger along the unfolded form or the folded form. And you can see the imprinted dots. It's actually double-sided Braille, which was pretty fun. And this is, again, designed with custom software and also a custom tool, because no one has ever printed Braille in a spiral, so there were no devices that could do this. And Alfonso jerry-rigged this Zund machine to manually impress each dot. It only takes about an hour per sheet to make a page. It's probably why people don't make Braille this way, but it's pretty awesome. I have a lot of fun with QR codes, which are a nice mathematical structure. They're error correcting codes, so even if you remove a big circle out of the center, you can still scan this and it will say folding error, predicting what's about to happen. A little diversion on QR codes. We've been experimenting with how far you can push them. It turns out you can print some text onto them with the right contrast and things still scan. This if you scan, it will go to the original text of Alice in Wonderland. And this is, of course, the Cheshire Cat. And the text here is when Alice meets the Cheshire Cat. And even more extreme, and I think this is on the poster for this event, you can remove about 8/9 of the QR code and it will still scan perfectly as a QR code, following the spec and everything. This is one that if you scan says, "Can't take my eye off of you," but it looks like just an image of this eyeball. And we've also been exploring how to make these out of paper. There's no folding here, but here we're cutting, in this case, 4 sheets of paper according to these patterns on the right, and stacking them up, and you get the QR code with a little bit of third dimension, which is kind of fun. Or here is an actual human fingerprint converted into a QR code that, if you scan, says my fingerprints are all over this. You can also play with color. The standard is quite unspecified as it comes to color, but you could just play with contrast and these will still scan. Each of them has a little fun message. You can even add more of the third dimension. These are wooden 3D QR codes, and from the right angle it will scan. In this case, I think it says, please scan this QR code in order to read it, which is useful if you've already scanned it. Well, maybe not so useful. And of course, we turn these back into curved crease sculpture. So this is a kind of QR code coloring book. You'd have to fill in the blanks here to make it into a QR code, fold it up into this paper sculpture. A couple more examples. We combining paper and glass. We can pour hot glass onto paper, burn a cool pattern, and then fold it into a curved crease thing. And then, of course, we can put that folded paper back into glass, and so we've gone full circle from glass to paper to glass. Our recent largest pieces. This is 14 feet tall. What is that? 7-8 meters. This is again designed with. So now we have hanging curved crease sculptures. Again designed with software to lay out. In this case, random arrangements of hand-drawn people. or in this case, various endangered animals in the world. And it's a new fun. We'd like going bigger, so this is our way to branch into the real structural origami side. Still just folding paper. And most recently, we've been collaborating with Win-Win, who's a fashion designer in New York City, origami fashion designer, and we've done some of the first curved crease dresses, which is pretty exciting. And been having a lot of fun playing with other materials. This is a big project to get them to fold, but hopefully more to explore. I think you've already heard about the idea of super collaboration, but because I made up the word, I'll talk a little bit about it again and close things off. Everyone there is having a lot of fun this week, coming up with different ways to solve our unsolved problems. People have come in with their whatever they have been thinking about. Unsolved problems are everywhere. You can think about anything in your everyday life, and there's probably an interesting unsolved problem, maybe a way to approach it with origami. But you can apply this technique not just to origami, to anything you're exploring. Take a big group of similarly interested people and just brainstorm together and have fun solving them. And if you want to learn more about it, you can go to this website. We also have software that we use to keep track of our progress and all of these things called Co-Author. It's freely available. So if you're interested in doing your own super collaboration workshop, talk to me. And that's it. Thanks.